Hello, this is a demonstration for the machine problem using the Bairstow method. So as I said from my previous video, so let's try to solve the problem in the actual Bairstow method application. So since we have the function of equal to x cubed minus 4x squared plus 3x minus 1, so we have to put here x 1, which is the value of x, and minus 4 comma 3 comma minus 1. So we have to put four values. So after we just click this one, we can easily see that the f of x is equal to 1, which is this one, because the machine is reading this value. So 1x cubed minus 4x squared, which is this one, plus 3x, this one, and minus 1. So that is how we put the value and convert it into, the machine is automatically converting it into polynomial expression. So now we have to assign the initial value of r, which is 0, and the initial value of s, which is also 0, and then here we have to put the absolute error 0.0075 as mentioned from my previous demonstration. So we have to put here decimal digits of 4, and after putting all the values we have to click the calculate. So now as we can see here, the first iteration we got all the value from for A0 to A3 and B0 to B3 and C0 to C3 using synthetic division. So we now got the linear equation, which is C underscore 2. This is actually C2 times the initial value of R plus C3 times the initial value of S is equal to minus B1. And here is C1 times the initial value of R plus C2 times the initial value of S, which is equal to minus B. So now we generated the linear equation, which is negative 4 times the changes of R, the value of changes of R, plus 1 times the value of the changes of S. I'm sorry, it's wrong. So this one is actually the minus 4 times the value of R initially, plus 1 times the value of S is equal to negative 3. So 3 times the value of R plus minus 4 times the value of 5, I mean the value of S is equal to 1. So now we got the changes of the value of R, which is equal to 0.8462, and the changes of S, which is equal to 0.3846, and we generate the absolute error value of R is equal to 100, and also the absolute error value of S is equal to 100. So using this new value of R, so we will use this one for the next iteration. So if you can see in the next iteration, we generate using the synthetic division, we generate A0 as negative 1, A1 as 3, A2 as negative 4, A3 as 1, B0 as negative 1.6072, B1 as 0.716, B2 is equal to minus 3.1538, and B3 is equal to 1. And also here the C0 is equal to negative 3.2157, the C1 is negative 0.8521, and the C2 is negative 2.3077, and C3 is equal to 1. So we get the linear equation of C2 times the changes in R plus C3 times the changes in S is equal to minus B1. So we get another one, which is C1 times the changes of R plus C2 times the changes of S is equal to minus B0. So we generated the linear equation of negative 2.3077 times the changes of R plus 1 times the value of the changes of S is equal to minus 0.716. We also have negative 0.8521 times the changes in the value of R plus negative 2.3077 times the changes of the value of S is equal to 1.6073. So therefore we got the initial the value in the changes of R is equal to 0.0073, and the changes in the value of S is equal to minus 0.6991. So we get the absolute error value of R, which is equal to 8547, and the absolute error value of S is equal to 222.2835%. So now we generate the new value of R, which is equal to 0.8534, and also the new value of S is equal to negative 0.3145. These values, we will be using this one for the next iteration. So in the third iteration, as you can see here, using the synthetic division, we generate the linear equation of C2 times the changes of R plus C3 times the changes of S is equal to minus B1, and C1 times the changes of R plus C2 times the changes of S is equal to minus B0. So we then again generated a linear equation of negative 2.2931 times the changes of R plus 1 times the changes of S is equal to minus 0.0001. So we have also negative 2.2715 times the changes of R plus negative 2.2931 times the changes of S is equal to 0.0103. So therefore we got the new value for the changes of R is equal to negative 0.0013, and then the changes of S is equal to minus 0.0031. So we then compute the absolute error value of R, which is equal to 0.1583, and the absolute error value of S is equal to 0.9903. And we now generated a new value of R, which is equal to 0.8521, and the new value of S is equal now to 0.3177. So using this value of S and R, so we can then compute in the fourth iteration. So as we can see here, there's a value of A0 up to A3, B0 up to B3, and C0 up to C1. So we then generated the linear equation of C2 again times the value of changes in R plus C3 times the value of changes in S is equal to minus B1, and C1 times the changes in R plus C2 times the changes of S is equal to minus B0. So we generated the linear equation, as you can see here, and then we get the value for the changes of R is equal to 0, and the value for the changes of S is equal to 0. We then get the absolute error for the value of R is equal to 0.0002, and the absolute error value of S is equal to 0.0004. So as you can see here, we stop the iteration because we already reached the terminating condition, which is 0.0075, which is the absolute error value. So using the new value of R, so we can then calculate the root formula using x is equal to R plus and minus the square root of R squared plus 4s all over 2. So we then now generated two values, which is values of x, which is 0.8521 plus and minus. This is the calculation, 0.8521 plus square root of minus 0.5446 all over 2. the same as here in the next in the other x, but we are using the negative sign. So we then generated the value of x, which is 0.246 plus and minus 3 uh, plus and minus 0.3691i. So using the synthetic division to reduce the degree of polynomials. So now we are currently in third degree. So as we can see here, we use the value of x, and here also we also use the another value of x, and then we generated the value of our new x, which is the negative 3.148. So we have to shift the other side. That's why it becomes x is equal to 3.148. So these are the three root found. So that's why there's nothing to rerun. So it means that all roots are found. So you don't need to rerun. So it's even not enabled here. So because we already found all the roots. So this is the demonstration for Bairstow method using third order polynomials. But actually there's no limit for this degree. So I tried up to 20, so it's keep on iterating, so there's no issue. But the limitation is you cannot put here initially as 0. If you put here 0, it will give you an error, and also if you put less than 3 here value, it will also give you an error. So the required value, we have to use the third order polynomials. So this ends of the demonstration for Bairstow method. So let's try now the regular Falsi. So as I mentioned before from my previous demonstration, let's now try to solve the problem, which is the transcendental function. So let's put here the cos, which is capital COS, open parenthesis, 4 times capital X, that's very important, plus log, which is capital L, small og, times capital X, it's very important also, minus 0.8. So this is how we put the function here so that our machine can solve the problem. This is the example of the transcendental equation. So let now check the range from negative 3 to 5, and let's try to click the check. So as you can see here, the fluctuation found, we got the f of negative 1 is equal to none, and f of 0 is equal to negative infinity, and then the f of 2 is equal to minus 0.2524, and then the f of 3 is equal to 1.1425. So as I use in my demonstration, I use the f of 2 and f of 3 as my x0 and x1. So let's now click OK, so we can put here the value. So now let's try to put here 2 and also 3. So we have also to put here the terminating condition, which is the absolute error value of 0.0001% and the decimal digits of 4. So now after completing all the values, after putting all the values, so let's now calculate. So as you can see here, so after just 6 iteration, so we satisfy the terminating condition, which is 0.0001. So now here it's 0. So this is the demonstration for the regular Falsi method using the transcendental equation. So let's clear the table and try another problem. Let's try the much easier. I mean the just the polynomial problems. So let's try to put here the x cube, which is to be written as po, open parenthesis, capital X, comma 3, 3, close parenthesis, minus 4 times po, open parenthesis, capital X, comma 2, 2, close parenthesis, then plus capital X minus 10. So this is how we convert the problem of x cubed minus 4x squared plus x minus 10. So the machine so we have to remove this one, sorry. So the machine can only read this value, so we can compute the problem. So let's put here the terminating condition as 0.0001, the same as before, and also the decimal digit of 4. So we also click here the range of -3 and 5. So now we then try to click the check. So as we can see here, we get the fluctuation found. F of 4 is equal to -6 and f of 5 is equal to 20. So now we also satisfy the bracketing condition. So let's click OK and put here 4 and 5. So after putting all the values, we can now click the calculate. So if you can see here, as I said from my another video demonstration, so after 7 iteration, we get the terminating condition of 0.0001. So that's why it's 0 here. So we now compute all the values. So we have here x0 and x1 and x2, which is the root, and then the f of x0 and f of x2, f of x1, and the absolute error. So this is how we solve the polynomial equation using the Regula Falsi. And this ends the demonstration using my machine problem. Thank you.